Welcome to G Fun Facts Online. In a world captivated by the allure of natural diamonds, a technological revolution is quietly unfolding in laboratories across the globe. Scientists, wielding the powers of extreme pressure and temperature, are not just replicating nature's most coveted gem, they are transcending it. They are creating diamonds that are chemically, physically, and optically identical to their mined counterparts, but they are also something more. They are a canvas upon which scientists can paint with atoms, engineering properties that are not found in nature, creating unearthly diamonds with functionalities that extend far beyond the realm of jewelry. Today, we delve into the fascinating world of extreme materials synthesis to uncover how humanity learned to forge diamonds and how these lab-grown gems are poised to reshape our technological future. The human fascination with creating diamonds is a story as old as our understanding of their fundamental nature. Our journey begins in 1797, when the English chemist Smithson Tennant made a pivotal discovery: diamonds are a pure form of carbon. This revelation ignited the imaginations of scientists. For over a century, they embarked on a quest to transform humble carbon, like graphite or soot, into the world's most prized gem. The late 19th and early 20th centuries were filled with tantalizing claims of success. In 1879, Scottish chemist James Ballantyne Haney reported creating diamonds by heating a mixture of bone oil, paraffin, and lithium in a sealed iron tube. Around the same time, French chemist Henri Moissan claimed to have synthesized diamonds by rapidly cooling molten iron saturated with carbon, a method inspired by the discovery of diamonds and meteorites. While these early attempts were shrouded in controversy and their results couldn't be reliably reproduced, they were not failures. They were crucial stepping stones, highlighting the immense pressures and temperatures that would be required for diamond formation. The modern era of diamond synthesis truly began in the mid-20th century, fueled by the Cold War drive for technological supremacy and a growing demand for industrial-grade diamonds. In the United States, Sweden, and the Soviet Union, systematic research programs were launched. The most famous of these was General Electric's Project Superpressure, which began in 1941. This ambitious project brought together a team of brilliant scientists, including Francis Bundy, H.M. Strong, and Tracy Hall. After years of relentless experimentation, a breakthrough was finally achieved. On December 16, 1954, Tracy Hall, using a new type of press he designed himself, successfully and reproducibly synthesized the first man-made diamonds. The experiment was a monumental feat of engineering. It involved subjecting graphite to a pressure of over 1.5 million pounds per square inch and a temperature over 2,000 degrees Celsius, all in the presence of a metal catalyst. The announcement of this achievement in 1955 sent shockwaves through the scientific community. It marked the dawn of a new industrial age. While GE was celebrating, they weren't entirely alone. Researchers at the Swedish company ASEA had secretly managed to synthesize diamonds a year earlier, in 1953, though they kept their discovery under wraps for many years. The Soviet Union also developed its own successful methods around the same time. These first synthetic diamonds were small and gritty, primarily suited for industrial applications where their exceptional hardness was invaluable for cutting, grinding, and drilling. The dream of creating large, beautiful gem-quality diamonds was still decades away. But the fundamental principles established during this pioneering era paved the way for the advanced techniques that are now producing a dazzling array of lab-grown diamonds that rival, and in some cases even surpass, their natural counterparts. So how is it done today? There are two primary methods that have been perfected to replicate and refine nature's process: high pressure/high temperature, or HPHT, and chemical vapor deposition, or CVD. Let's start with HPHT. As the name suggests, this method directly mimics the conditions under which diamonds are formed deep within the Earth's mantle. It is the original technique, refined from the work done at General Electric. The process begins with a diamond seed, a tiny microscopic fragment of a pre-existing diamond. This seed acts as a template, a blueprint for the new diamond to grow upon. This seed is placed in a capsule along with a source of highly pure carbon, typically graphite, and a metal catalyst, such as iron, nickel, or cobalt. This entire capsule is then placed inside a massive press. There are a few different types, like the belt press, the cubic press, or the Russian bars press, but they all do the same thing: generate almost unimaginable force. Inside the press, the temperature is cranked up to between 300 and 600 degrees Celsius, and the pressure is increased to over 870,000 pounds per square inch. That's about 5 to 6 gigapascals. Under these extreme conditions, the metal catalyst melts, forming a molten bath. This liquid metal dissolves the graphite carbon source, just like sugar dissolves in hot tea. The dissolved carbon atoms then migrate through the molten metal towards the slightly cooler diamond seed. There, they crystallize onto the seed's surface, latching on one by one, perfectly replicating its diamond lattice structure. A new, larger diamond is literally grown, layer by atomic layer. The entire process can take anywhere from a few days to several weeks, depending on the desired size and quality. The result is a rough diamond that is then cut and polished, just like a mined diamond. The technology has advanced incredibly. Early HPHT diamonds were often yellowish due to nitrogen impurities. But today, with ultra-pure materials and precise control, scientists can produce large, colorless, high-clarity diamonds that are often preferred for their pristine quality. The second major method is called chemical vapor deposition, or CVD. If HPHT is brute force, mimicking the Earth, then CVD is a more delicate process, like painting with atoms. The CVD process begins not with a tiny seed, but with a thin slice of a diamond crystal, which is placed inside a vacuum chamber. The chamber is then filled with a mixture of gases, typically methane, which is rich in carbon, and hydrogen. Then, a source of energy, usually a microwave beam, is used to heat the gases into a plasma state, reaching temperatures between 800 and 1,200 degrees Celsius. This superheated plasma is a chaotic soup of atoms. The methane and hydrogen molecules break apart, releasing individual carbon atoms. These freed carbon atoms are then drawn down towards the cooler diamond seed plate. As they land on the surface, they arrange themselves into the diamond crystal structure, continuing the pattern of the seed. The diamond grows, one atomic layer at a time. The hydrogen gas plays a very clever and crucial role here. It acts as a cleaner. If any carbon atoms try to bond in the wrong way, forming graphite instead of diamond, the hydrogen selectively etches them away, ensuring the growing crystal remains pure diamond. CVD is a slower, more controlled method than HPHT, often taking several weeks to grow a sizable diamond. But its major advantage is that it operates at much lower pressures, making the equipment less expensive and the process more energy efficient. It also allows for incredible control over the incorporation of impurities, which is key for creating some of the unearthly diamonds we'll talk about in a moment. But the ability to create diamonds in a lab isn't just about replicating nature's beauty. It's about surpassing it. Scientists can now create diamonds with properties tailored for a new generation of technologies. Naturally colored diamonds are exceedingly rare and expensive. A yellow diamond gets its color from nitrogen atoms trapped in the carbon lattice. Boron atoms create a blue hue. In the controlled environment of a CVD or HPHT reactor, scientists can play the role of Mother Nature with incredible precision. By intentionally introducing nitrogen gas into the chamber during growth, they can create vibrant yellow diamonds. Adding boron creates stunning blue diamonds. They can even create pink and red diamonds through special post-growth treatments that alter the crystal structure, and green diamonds by exposing a finished stone to a controlled dose of radiation. This makes beautiful colored gems more accessible, but more importantly, it allows for the creation of diamonds with specific optical and electronic properties. This is where we enter the quantum frontier. Perhaps the most exciting application of lab-grown diamonds is in quantum computing. The building block of a quantum computer is a qubit. One of the most promising candidates for a stable, reliable qubit is a specific defect in a diamond's crystal lattice known as a nitrogen vacancy, or NV center. An NV center is created when a nitrogen atom takes the place of a carbon atom, right next to a spot where a carbon atom is missing, a vacancy. This tiny imperfection, this combination of a nitrogen atom in a hole, creates a tiny, isolated quantum system. Its quantum properties, like spin, can be controlled with lasers and microwaves. The genius of the NV center is that it's perfectly protected by the rigid, non-reactive diamond lattice around it. This protects it from outside noise, allowing it to maintain its delicate quantum state for a relatively long time, even at room temperature. This is a huge advantage over other qubit technologies that often require cooling to near absolute zero. By precisely implanting these NV centers into ultra-pure, lab-grown diamonds, scientists are building the foundations for quantum computers that could revolutionize medicine and materials science. These NV centers are also being used to create incredibly sensitive quantum sensors that can measure magnetic fields, temperature, and pressure at the nanoscale, opening up new possibilities for medical imaging and geological exploration. The rise of lab-grown diamonds is also having a massive impact here on Earth. For over a century, the diamond market was controlled by a few large mining companies that managed supply to keep prices high. Lab-grown diamonds, which can cost 20 to 40% less than a mined stone of the same quality, are completely disrupting this model. This is because the supply chain is far more efficient, with costs driven by electricity and equipment, rather than massive mining operations. This has led to a dramatic shift in consumer behavior, especially among younger buyers. But this disruption also poses a challenge to the economies of countries like Botswana, which are heavily dependent on diamond exports. Beyond the economics, there is the environmental and ethical calculus. Diamond mining can be incredibly destructive, requiring the removal of vast quantities of earth and using enormous amounts of water and energy. The industry has also been plagued by the issue of conflict diamonds. Lab-grown diamonds offer a compelling alternative. Studies have shown that mining a diamond can produce thousands of times more waste and use many times more water than growing one in a lab. While lab-grown diamonds are energy-intensive, many producers are now shifting to renewable energy sources to power their facilities. And because their origin is a controlled laboratory, they are inherently conflict-free and fully traceable. The creation of unearthly diamonds in the lab is just the beginning. We are standing on the cusp of a new material age, where we can design materials with precisely tailored properties to solve our biggest challenges. The same techniques used to create diamonds can synthesize other novel materials, like new super-hard substances even tougher than diamond, or high-temperature superconductors that could enable ultra-efficient power grids. The journey to create the perfect diamond in the lab has been long, but it has taught us a profound lesson. The materials of the future will not be discovered, they will be designed. The diamonds sparkling in our laboratories are a brilliant reminder that the future is not something we wait for. It is something we create, one atom at a time.